All right, so today we are talking about convolutions, which is your lab this Saturday. Hopefully a lot more will make sense after today's lecture. So let's dive right in. Yeah, something to keep in mind for this lab, we're getting into labs which will take time to train, and so you can't start the lab at 6 p.m. on Saturday night. That's not going to work. So just something to keep in mind, start early. You know, sometimes there are GPU limits on collabs, so you're less likely to run into those close to a deadline if you start a week before the deadline. Yeah, Olivia. Dim these lights? Yeah. Okay. So convolutions. Watch a video. So what we're looking at here is we're seeing an input image, and then we're seeing this filter glide across the image. This filter is a set of neural network weights. So convolutions are different from the normal fully connected neural networks that we've seen so far, because the weights of the neural network are localized in a spatial region. And because of that, they are able to learn spatial relationships in things like two-dimensional images. And so you can see each of these different filters that we've been looking at detects different types of features in the input image. And so look at these and see if you can maybe identify what types of features each of these filters was recognizing. Okay, we're going to pause the video. So each of these represents an output from a different filter gliding over this input image. Do you notice any patterns in the areas that got highlighted in these with these different filters? And when I say things that got highlighted, I mean features of features of the input image that could potentially be useful. Yeah. Looks like totally, yeah. It looks like the red in this first filter map. Yeah, it looks like the red is detecting top edges where it goes from white to black. Good observation. Yes, and the green is opposite. Yeah, so yeah, we see then going from white to black on the bottom is highlighted. Good. Anything else? Yeah. You're talking about this one? Yeah. Yeah, so in this bottom left filter, yeah, we're seeing, it looks like, yeah, we're also looking at edges, black to white, but then we're going left to right in this filter map. So that left edges are highlighted in green and right edges are highlighted in red. Yeah, cool. And so you can see that we did several layers of that and then matched the final activation map against a series of templates or prototypes that might sound a little bit familiar. And we classified that image as the letter A with about 92% confidence. So that's what we're going to go more into detail of how this works, but that's just kind of an intuitive sense of what's going on here. So this is another visualization. So this is going to be a different type of visualization, which showing what these convolutions, what is learned by these convolutions by a slightly different process. The process they follow in this.
We see advances in neural networks that enable computers to better see and understand the world. They can recognize school buses and zebras, and can tell the difference between Maltese Terriers and Yorkshire Terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside neural nets. In the top left corner, we show the input to the network, which can be a still image or a video from webcam. These black squares in the middle show the activations on a single layer of input. In this case, the popular deep neural network called AlexNet running in Cafe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, the unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over, responds to edges in the opposite direction, dark to light. Using optimization, we can synthetically produce images that light up each neuron on the site to see what each neuron is looking for. We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized produced by activation. By the time we get to the fifth convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different kinds of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulder. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for high activation, computed via the deconvolution. This feature responds to multiple phases in different locations. And by looking at the decon, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backdrop or decon, we can see that this unit depends most strongly on a couple units in the previous layer of con before, and on about a dozen or so in con 3. Now let's look at another neuron on this slide. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt. And smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting neuron. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool because we never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer. So the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the DeepViz toolbox and a few of the things we've learned by using it. You can download the toolbox in this URL and explore it for yourself. If you'd like to share what you find, you can use the hashtag DeepViz. Thanks for listening, and we look forward to seeing what you discover. Recent advances.
Any thoughts or comments on that video? Things you noticed? Yeah. Yeah, exactly. I think that's probably the most important point of this video is that, yeah, none of those features that were being recognized were labeled in the data set explicitly. The data set had labels like person, bookcase, school bus, etc. And in order to classify those things, it learned all of those immediate features. And you think that some of those were probably helpful for multiple classes, like, I don't know, for example, technique, hair or fur might be helpful for detecting bunnies and also wolves. So yeah, pretty amazing stuff. And that's really the power of deep learning. Like imagine trying to hard code an algorithm to classify wolves or classify bunnies, but yeah, deep neural networks are able to learn these hierarchies of features that are very interpretable and these high accuracy classification. Yeah.
How does the convolution layer learn? Because it's not like our nodes where it can just go up or down in this direction, but like they have certain amounts of, they're how can it change the parameters? They're a lot more analog, they're a lot more digital.
Yeah, so the question is how it's a great question. How do these convolutional layers actually learn? Because they're not all connected like we have in our fully connected networks. And it's actually what convolutions end up being in fact are sparse, extremely sparse versions of fully connected layers. And so they learn in exactly the same way, but the fact that we use convolutions basically gives our neural network this really helpful hint of spatial relationships. It groups these, for example, 9 pixel fragments together, and it turns out that is extremely helpful for it's a very extremely helpful architectural shortcut to learning image classification, in which those spatial relationships between pixels are really. And so yeah, as a result, we're able to train convolutional neural networks with the same number of parameters that a fully connected network would have taken, but which are much better than the fully connected network for image classification because we both that spark. So let's take a look at how this looks. So we're going to start with an input image, and it will be 32 pixels high or 30 pixels wide, and then it will have 3 channels. Does anyone remember what those represent? RGB. Yep. So and then each individual number in this 3-dimensional filter will represent the intensity of R, G, or B at that spatial location. So then our convolutional neural network is 5 by 5 by 10. We will call it filter. It's this other sensor. And in this sensor are learned weights. So rather than having a weight tensor that is 32 by 32 by 3, we're going to only be 5 by 5 by 10. And instead of applying that filter to the full image, we are going to scan it over. Let's see how that looks. And yeah, this is just a comment that each of these filters you can use the height and width function with the number of channels always equal to the number of the previous. Exactly. Yeah. The whole innovation of convolutions is like this. So you remember for normal neural networks, we take the dot product between the input vector and the weight matrix. And we do basically the same thing here, except we only take that portion of the input. We only take a 5 by 5 by 3 of our image, and we stretch that out. That 3-dimensional tensor into a vector that has length 5 by 3 is 55. And then we use the dot product, which we can stretch out the image, then stretch out filter, and we get a single number. So there the result of the dot product between the filter and a small 5 by 5. Any questions on that? Yeah. You and then. Good question. So the question is whether as you scan across the image, are you a step 1 pixel at a time or 5 pixels at a time? And the answer is you can go. You can do either one. That's what we just described is called the prime. We'll talk about that in a couple of slides. But your step size for each word has applied to the prime. Okay. Why? So the question is why does that is that for you? And the answer is if you want to have them line up, if you want to be able to cross product, you have to have the same number of numbers in your image. You could imagine a convolutional filter that works by only having the depth of 1, and that would combine filters combine filters from 1. But if you think about it, it's probably helpful to make between channels because it's only we don't see black and white. Having color helps identify. So basically, by having all 3 allowing for filters to see all 3 channels, we allow our filters to color. Huh? So the stretching out into a 1-dimensional vector, it's I mean you could also think of it as you point-wise multiply every entry in this filter with every entry in exactly the image, and then you get some of that. You don't necessarily need to do a operation. It's the reason we have the channels just has to do with what we are allowing our to see in that. Okay. Good question. We haven't gone there yet. So the question is, once we get this number, what do we do with it? We're gonna get them. Yeah. This. Yeah. Yeah. So the question is, do you have more than one filter for each layer in our letter? And the answer is yes. Yeah. See that in a second.
I see why this is useful for like picture data or like spatial proximity companies that are spatial data vectors. We had like non-spatial correlated data, or let's say like higher dimensional data.
So the question is, how would this apply to something that's not images? I would say that I would only expect convolutions to be useful in a setting where you have a spatial relationship between your inputs. And that's not necessarily limited to images. For example, if you imagine you have audio, just like a WAV file, and you want there's significant information in the relative location of those what we call them, data points in the sound wave. And so that would be an example, another example of where convolution could be useful. Also text, like written text. Again, proximity and relative position matters a lot.
Use it in your text.
So yes, I kind of agree with it. I do not. And the reason actually is because convolutions were kind of like they kind of had their day from like 2010 to 2017. And since then there's an architecture called transformers, which is used which feeds ends in a lot of tasks. And so most of my stuff uses. Yeah.
So in like
Oh, good question. Yeah. So for the case of audio or text, that's exactly right. The filter would no longer be 2-dimensional. You only have one spatial dimension. which is just time. And so, yeah, it would be a 1 minute. Yep. Yeah, Matthew.
I'm just curious about this. So I thought that that convolutional neural networks, at least different, more modern forms of them, are still used for image and video based learning projects. It's just that they aren't really used as often for things that are better suited for like data networks.
Yeah, I mean, CNNs are definitely still in use, for sure. Yeah. It's not like they're completely obsolete. But yeah, transformers have taken over a lot of things that CNN have previously. I think I saw one more question at the back. Not, we'll move on. Okay. Oh, sorry, Olivia. Yeah, we're going to transformers. That's the benefit of this class is I mentioned this before, but like this class covers what would be covered by like 6 classes. So we're going to learn about like CNNs, RNNs, transformers, deep reinforcement learning, the GANs, diffusion models, which are kind of a big thing of only the last year or two. And so yeah, the curriculum of this class is consistently evolving and getting more and more compressed. So you guys are getting a lot of things pretty well. Yeah. Okay, so let's keep going. So we get one number from taking the dot product of this filter with one region. Okay? We're not just going to do that with one region. Okay? We're going to slide over that filter, do that dot product again, get a number, slide it over again, get another number, and do that across the entire image until we created what we call an activation, which represents the areas, the different regions of this image that activate that particular filter. And then we can choose another filter. This is a question about multiple filters. Yes, we can. This is our second filter, and that will create a second activating net. And so we have, for example, 6 3x3 filters. We end up with 6 activation nets. And the input to our next layer is 28. That 28. Good question. Yeah. So the question is where and it depends on several things. It depends on the size of your filter, because if you have a 3x3 filter starting in the corner, the center pixel of that 3x3 convolution will be in the second row and column of the image. If it was a 5x5, it would be the third, the center pixel would be the third row and column of it. And so if you go with this week, for example, if our filter was 32 by 32, you would only have a 1 by 1 as there would be nowhere to slide it. So that's one thing is the size of your filter. Another thing that affects it is your stride. So in your stride is how far you slide your filter over each time. Imagine if you skip every other filter, every other pixel, we slide over 2 at a time instead of 1 at a time. This will be 4 by 4. So filter size matters, stride matters. Also, there's this thing called padding. Padding is adding 0 pixels at your image so that you can preserve, so that you don't really have a problem with your. So it's pretty common to add padding that makes it so that your convolutional filter, its center pixel is at the very corner. So for a 3x3 filter, you want to add 1, which would place the center pixel of your filter at the corner of the image. And then if you were doing stride 1, you would have 32. If your filter was 5x5, you would have 2, have that center pixel of that filter. So 3 things that affect the change are filter size, padding, and stride. We have a couple of I was going to ask, you also like pick up the of the right? Yeah, so the question is, can you also read kind of with that? That can definitely be a possibility. I've also seen things where they wrap the pixels, so they take pixels from one side and they put them on the other. Kind of information technique. Yeah. Good question. That's a great question. The question is, does having ever caused weird I would argue probably yes, because in a way you're allowing your network to see what the order of the bit is, which helps some information. Maybe a classification example where knowing where that. Yeah, like it's not a negligible operation. You definitely could be zero for all that. Yeah, what things am I allowing my network to exploit? That's a good opportunity to think that. Okay, so this is an example of actual numbers, but I am going to do my own example, which I like better. So we're going to right now design a train convolutional filter to recognize the number 7. Okay. So our input image is going to be the number 7, and we are going to assume that it's a black and white image. So instead of 28 by 28 by 6, we will say it's 28 by 28 by 1. And so we're going to design a 3 by 3 filter. And we're only going to put 1s and 0s in this filter. And we're going to assume that, yeah, this not only is this a black and white grayscale image, it's a black and white image. So it only has 1s. And so I'm going to actually rewrite this. We'll make this 7 a 5 by 5 image. And then I'm just going to color in the pixels representing 1s. And so as I'm doing this, think about what kinds of features you might want to have in, or what you might want a filter that recognizes 7 to run. Yes. Oh, cool. Yeah, so I'm gonna go across this 3 by 3 filter, and you tell me which entries to fill in. Cool. Yeah, I like it. Any other features that would be helpful? Yeah. Horizontal lines. Yeah, I like it. The horizontal lines or diagonal lines, we can make a new filter. Okay, tell me what to put left to right.
I guess.
Okay. Cool. Anyone else have an idea? Diagonal, yeah. So we'll do that. Okay, so let's scan these filters across the image. So what? Can I get a volunteer actually to do this with me? Yeah, okay, so we're going to start with the first filter, which will produce an activation map. And we will, let's do no padding on this example. So our output will be 3 by 3. So, and while our filters and our input are binary, we're going to get actual integers for the output activation maps. So first, we are going to take this filter and convolve it across the top row of this input image. So what would we get if we were to take the dot product of this filter with this top row? That is correct, yeah. And so he said that only one square matches up, and that's correct. That's the middle square, the middle pixel of the filter corresponds to the middle pixel of the top left corner of the image. Let's slide it over one and do it again. What do we get? He said that will also be a 1. That is correct. Okay, then one more. That is correct. Any questions so far on how we got those numbers? Michael.
So would there only be weights for those dark weights?
So the question is, would there only be weights for the dark and bad values, and would everything else not have weights? No. I just made those darkened values. The darkened values are 1s, and the other values are 0s. All of those are learned weights. I just did 1s and 0s for simplicity. Yeah. Yeah. Question.
Yeah. Go through that.
Yeah. So to get the first one, we looked at matching this filter with the top 9 pixels, top left 9 pixels of the image. Got that? Yeah. So how did we get a 1 from that? So the top left of the filter versus the top left of that region is 1 times 0. And then the top middle of the filter times the top middle of that region is 1 times 0, 0 again. And the top right of that filter is 1 times 0 in the region, 0. Then the middle left of the filter is 0. The middle left of the region is 1. 0 times 1 is 0. The middle pixel of the filter is 1. The middle pixel of the region is 1. 1 times 1 is 1. That's where we got our 1. And then everything else ends up being 1's times 1's. There's always going to be a 0 multiplied in there at some point. And then, yeah, you go on. Looks like you got it as you, same deal as you go across. And I think as we're going to move down the road, we're going to start identifying some the features we were looking for. So, yeah, going down to the next row, what is going to be our dot product? 3. Let's see. Yep, that is correct. And then slide over 1. 5. So that filter is lining up. Then over 1 more.
2.
2. Then slide down 1.
3.
3. All right, so you can kind of see how that filter in the activation map, the region that that most activated that filter, what got the highest number of activated map. And we can do a similar thing for our horizontal line detector. And I'll just do this quickly. So what would you get for our first one?
3, 3.
3, 3, 2. 1, 1, 1, then 1, 1, 0. Okay, so this is going to be kind of tricky now. So now we are going to design a two-dimensional filter, and we're just going to leave off the diagonal line for now. We're going to now design a two-dimensional filter that looks for sevens. Okay, and we're going to make this a 2 by 2 by 2 filter. So what it will look like is this. Does it make sense how I'm drawing a 2 by 2 by 2 filter right now? So this is a three-dimensional tensor that I'm representing as two-dimensional matrices. And the first matrix will correspond to the first channel, and the second matrix will correspond to the second channel. Okay? So what might we want this first actually, you know what? We are going to make this these 3 by 3 by 2, so that we can get a single number as our final output. So what numbers do you think we might want in this 3 by 3 by 2 filter to recognize sevens? How about in this first channel? What do we want there? You want the very middle pixel to be high. I like it. In fact, let's just say 1 in the very middle and zeros everywhere else. How about this other filter?
1 in the first 2, 0.
1 in the first 2, zeros otherwise. I like it. So now our convolutional operation is going to look a little bit different, because instead of involving a one-dimensional filter or a filter with one channel over an image with one channel, we're now involving a filter with two channels over an input with two channels. So can someone give me the result of involving channel 1 of the activation map with channel 1 of the filter? It's 5, yes. And that came because we multiplied 1 by 5 and 0 by all of the other numbers and summed those up. How about for the bottom? 6, exactly. So we get that by multiplying 1 by 3, 1 plus 1 by 3, plus 0 times everything else. We get 6. And so then the final result of that convolution is 5 plus 6 is 11. And that is the score of our very simple neural network for the number 7. Yeah, question. Yes, you want an explanation to the second filter where we had 2, 1, followed by all 0. Yeah, so for the first filter, we chose these numbers based on what regions were activated by our setter. So we thought, oh, the corner detector activated the middle. We want to highlight that middle. We thought, oh, the horizontal line is activated on 2. We want to highlight this one. Yeah. So with this there, so the question is whether the multi-dimensional convolution layer is not a pooling layer. It's similar to a pooling layer in that it reduces the size of the output, And so I might call it a reduction layer, but a cooling layer is something that, yeah. 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 How are we involving a filter? So we start with the filters in the top left corner of the equipment. And then we slide it over one pixel to the right, and one more pixel to the right. Then we go to the next row, and go down a pixel, and go all the way back over to the left. And then slide it right. Does that make sense? Yeah. Yeah. But you're wondering, yeah, for terminology, so we have our filters, we have the learning phase, and then our what I'm calling the activations are the outputs. Yeah. Yeah, great.
In the third lab, we're making convolution, but before a bunch of pretty much all already made.
Yeah.
So we don't actually decide what any of the filters are. It sort of learns it over time.
Correct. Yeah, so yeah, that's a great question. In this scenario, we designed these filters kind of but in practice, this would be learned through back propagation over time and neural network. We are out of time. So if you have any more questions, come up and talk to me after class.